Hello, everyone. My name is Paweł Guzewicz, and I'm going to present efficient exploration of interesting aggregates in RDF graphs. This work has been done under the supervision of my supervisors, Ioana Manolescu and Jan Lediao, and in collaboration with our colleague Miliana Mazura. Suppose that you want to explore some public datasets in the form of a graph. While browsing the internet, you stumble upon the linked open data cloud, and you see this diagram. Every node represents one dataset, and edges are the links between them. Then you ask yourself, so what's in a graph? A few seconds later, you realize that you don't understand anything, yet it looks quite interesting and worth exploring, so you want to give it a go. Consider a journalist who wants to write a news article and looks for an interesting lead. They may explore public data, frequently available in the form of a graph. The data may contain interesting insights that can become leads. Our goal is to help the journalist find such interesting insights in the graph. This task is called computational lead finding. So how do we do it? Well, we focus on exploring large heterogeneous RDF graphs like this one about chief executive officers. For instance, the journalist can analyze CEOs from different countries and their political connections. We run analytics over such graphs to find interesting leads. In this work, the interesting leads are aggregates. We can plot a heat map of average age of CEOs based on their nationality and the number of companies they manage. In this complex graph, we observe an interesting insight. The Angolan CEOs managing two companies are on average younger than those in other countries. It turns out that this age phenomenon is due to Isabel dos Santos. She's a daughter of Angola president. The journalist can use this insight as lead to write a news article. In essence, this example illustrates how we find the most interesting aggregates in the graph. We aggregate the RDF data along many dimensions. Each such multidimensional aggregate consists of a candidate fact set, a set of RDF nodes over which we aggregate, a set of dimensions, a measure, and an aggregate function. Notice that we use direct properties present in the graph, as well as derived properties, which we derive from the data ourselves. To quantify the interestingness of an aggregate, we apply an interestingness function over the aggregated measure values. Our system natively supports variance, skewness, and kurtosis as interestingness functions. Variance, for instance, detects outliers present in the data, such as Angolan CEOs with low average age. We rank aggregates based on their interestingness score. Finally, our problem statement is the following. Given an RDF graph G, a positive integer k, and an interestingness function h, we want to automatically find the top k aggregates A1 to AK whose interestingness on G is the highest. Now you may wonder, okay, so why is this problem hard? Given the goal to find the top k most interesting aggregates in an RDF graph automatically, we need to tackle two main challenges. First, we need to decide which aggregates to choose. RDF graphs lack schema, so we need to find facts, dimensions, and measures ourselves. Further, we need to derive new properties to explore more candidate dimensions and measures. This leads to a large and rich space of candidate aggregates. Our second challenge is then to evaluate the aggregates correctly and efficiently. We aggregate over multiple dimensions, and thus we construct n-dimensional aggregate lattices. Classical relational group by cube aggregation fails to provide correct results on RDF data. Finally, we want to improve the runtime by avoiding computational effort on uninteresting aggregates. We can divide the contributions we make in our paper into two parts. First, we describe our approach. We present the architecture of our space system. Then we provide new, correct, and efficient multi-valued data cube algorithm that computes n-dimensional aggregates lattices on RDF. And finally, the early stop technique that allows us to prune uninteresting aggregates. Second, we show why our approach is good. We discuss our experimental analysis. We present interesting aggregates that Spade found in the real data. We show the correctness of our approach. At last, we analyze the efficiency and scalability of Spade. Let me now conclude this short talk and comment on the lessons learned. I introduced a Spade system, an extensible framework for finding the top k most interesting aggregates in an RDF graph. To the best of our knowledge, Spade is the first system that explores complex RDF data without a clear schema, with many ways to choose facts, dimensions, and measures. Furthermore, our novel MVD-cube algorithm for aggregate lattice evaluation is the first correct group-by-cube algorithm for RDF data with many multivariate dimensions. MVD-cube is efficient, and it is even faster than the Postgres cube. Finally, our new early stop technique provides further speed up thanks to aggregate pruning with probabilistic guarantees. For more details, please refer to our full 20-minute video and the paper. Thank you for your attention.